I'm going to be talking about containers for no profit. So if you want to follow the slides along, or I don't know, you can find them here. And yeah, let's get, about me. So I'm a software engineer at Tarides. We work on unikernels and OCaml build systems. I also attended Recurse Center in spring 2019, where I first learned about Rust, and it's the best programming community there is. And I'm also a co-organizer for Bang Bang Convest, which has talks about the excitement and joy of computing, and we have our CFP open soon. So this talk is divided into, I want to talk about three main things. So one is, what does it mean to be a systems programming language? And what makes Rust a good candidate for a systems programming language? And what are containers? And how do you write your own container? So the thing that you hear a lot with Rust is how it's a new systems programming language, and it's revolutionizing somewhat the systems programming world. But what makes it a good candidate, and why are C and C++ and Rust systems programming languages, and Python and Perl not systems programming language? So I will take you through the evolution of systems programming languages. So I'll start with 1970s, where this was the time when the term computer systems was first coined, and there was an effort of defining what computer systems actually meant. And in the paper, Bergeron says that a systems program is an integrated set of subprograms which exceeds some complexity. So typical examples of these systems would be systems for simulating or translating or time sharing. And then the paper then goes on to define what a systems program looks like. So it's likely to be used to support other software programs. So for example, most applications read from or write to files on disk. So these operating system would be written in a systems programming language like C, provides this functionality. So it makes sure that you have the permissions to access the file, and then if multiple programs are handling this file, they handle it correctly, and then loading blocks of files into memory, and then writing to memory, and so on. And then it's likely to be continuously evolving, so it's not a one-shot solution. You will keep building on top of it. And while these ideas are very descriptive, the key idea of this paper was very prescriptive, which was to separate the low-level languages at the time, which was assembly, with systems language at the time, which was Fortran. And then it says a systems language, a programming language, is a language which you can use without a concern for bit twiddling. So a high-level language, which was at the time Fortran, should be able to have the conciseness and readability, and designing and debugging and writing this application should be minimized without imposing the necessary overheads on the resources. So, and the last entry in the 1970s is this paper called Systems Programming, which asks the question, what is system programming? So the computer is essentially following a set of instructions which are fairly primitive. So if you want to give more complex instructions, so if you want to say, if I have x equals 30 into y, and I know that y is 10, so what is x? Give me x. So presently, computers cannot understand these instructions without something between the hardware and you specifying those instructions. So you need systems programs like compilers, assemblers, loaders, and macroprocessors to to make the computers understand the needs of their users. And then there was the 1990s, where it was the rise of scripting languages. So in the 70s and 80s, most people saw systems programming as a contrast to assembly programming, because there were simply no other tools to build systems. And in the 1990s, there was a sea change in programming languages with the rise of dynamically typed scripting languages. So Bash and Perl and Ruby, and all of them worked their way into the mainstream. And systems programming languages were designed to build more primitive computer elements, starting from words of memory, and scripting languages were designed for gluing. So you can separate the scripting languages and the systems programming language on the axis of type safety instructions per statement. So if you would have static typing in systems programming languages, because they make it easier to build complex systems, whereas the scripting languages would be dynamically typed so that it's easier to glue two complex components together. And then in the 2010s, massive resources were poured into just-in-time compilers for JavaScript, and so JavaScript's V8 and Python's PyPy. And while their performance was not equivalent to traditional systems programming languages, they were fairly competitive to C and C++. And and large-scale distributed systems like Spark are written in Scala, and new programming languages like Julia and Swift and Go are pushing the performance boundaries on garbage-collected languages. And Dropbox was able to build a large scalable system on just Python, and JavaScript is used nowadays to render billions of web pages. And there's gradual typing in JavaScript and Python that's helping write production code today. So then the question is, in 2019, what is a systems programming language, since the boundaries are so blurred? The thing with languages in the category of C, C++, and Rust is they're distinguished in their level of abstraction from the machine. So these languages expose the underlying hardware, like memory allocation and layout and fine-grained resource management. So the question to ask is, if you have an efficiency problem, does the language give you enough tools so that you can identify the bottleneck by careful control over the machine? So in the same way, when you have a statically typed language and you say, oh, I'm adding these two integers, and they're most definitely integers, the languages in the category of C and Rust give you the confidence that this code will execute on this machine just as I intended it to. So what the systems programmers today should be identifying is what ideas in system design we could use to adapt to the reality of modern hardware. And this is where Rust shines, because the Rust takes really good software design and functional programming principles and applies them to lower-level problems like futures and error handling, and of course, memory safety. So we should also consider the additional benefit that are enabled by Rust type system, which is program analysis and information flow control, and also safe traversal of pointer-linked data structures. And you can throw all of that out of the window, and systems programming is just when you read more man pages than you read the internet. And then, so we move on to the next part of the talk, which is writing our own container. So before we write our own container, we should ask the question, what even is a container? So Is a container a process, or what's Docker? Are Docker containers? It's very confusing. So the word container doesn't mean anything really precise. It's a bunch of Linux kernel abstractions put together, which lets you isolate a process from each other. So when you use those features together, you call it a container. And these features of the Linux kernel let you pretend that you have something like a virtual machine, except that it's not a virtual machine at all, and it's just processes running in the same Linux kernel. In a talk called Containers Operating Model, Alice Goldfuss defined containers as processes which are born from turbols, anchored to namespaces, and controlled by cgroups, so when you're specifying a Docker file or like some sort of container config, you specify the environment and the file structure of your application, and when you build that Docker file, you're making a tarball, which then gets deployed, unpacked, and is then run as a process, like any other process on your host. If you deconstruct the container, it would be actually really nice if creating container was as simple as having a syscall says create container. I just created a container, but it's not. But it's still fairly simple because there's 3 things that make up the majority of magic of the container, which is chroot, namespaces, and cgroups. Chroot is simply changing the root directory of the current process and its children for isolation. So once you chroot into like a new root, for example, you can't break out of that jail. So it can't access anything else on the machine. So it's a thin wrapper around like a similarly named syscall, and it allows you to restrict a process's view of the file system. So if you wanted to chroot in Rust, what you would do is you would bind a new root and set the current directory to the new root, and then you have isolated yourself so that you can't look outside your current view of the system. The next is namespaces. So Linux namespaces were inspired by a wider named functionality that is used heavily throughout Plan 9 from Bell Labs. So just as chroot allows processes to see any directory in your system as an arbitrary root of the system, independent of the rest of the processes, namespaces allow other aspects of the operating system to be independently viewed. So this includes process tree and networking and mount points and IPC, interprocess communication resources, and so on. So you have multiple namespaces, like the PID namespace. So in a PID namespace, you become the PID1, and then your children are the other processes. And in all other programs, when you move namespaces, all other processes in that namespace are gone. When you have a new networking namespace, you can run programs on any port you want without conflicting with what is already running on another namespace. On the mount namespace, you can mount and unmount file system without affecting the host file system. So you can have a totally different set of devices mounted. So creating namespace is as simple as calling a clone syscall, and then once all the processes of the namespace exit, the namespace is destroyed, and you can enter an already existing namespace using setns system call. And if you want to do that in Rust, it's using Nix crate, which allows you to use the unshare system call, which separates the namespace from your current parent and creates a new system call where I say I have a new time sharing namespace, a new PID namespace, and a new, I forgot what new NS stood for. But I have these new namespaces, and now I am separate from the root. And I will start as when I start this new container, I will start as PID1, and all the children in this container will be will have the PID starting from there. And the last component of the container are cgroups. So we have a new magical world with new processes and sockets that are separate from our old world. But what happens if the processes running in this part of my world consume all the RAM and all the resources, and which means that everything outside this magical world is not so magical? So cgroups come to the rescue here. So you can limit the amount of memory your programs can use, or you can say that the maximum processes that can run in this container are 5. So once you exceed 5 processes, you cannot start any more processes. And then it also allows you to create a hierarchy of the processes, and the resources and the usage of these groups can be limited, and it's implemented through a pseudo file system called cgroupfs. So if you go look in sysfs cgroups, you can literally see all the files where you will have a file where it will say PID max, what PID max is, and then you can say, OK, 20, and then you won't have more than 20 processes in that cgroup. So subgroups in the cgroup inherit the limits set on the parent group. So if you have a container where you say, I have 20 processes, and then you spawn something in that container where you say, oh, but I can also have 100 processes, you cannot do that because the limits of the parent group said you can only have 20 processes. And a process can only be a part of one cgroup, so that there's no contention between what the limit set is. And a subsystem controls each resources. So there's a memory subsystem, which controls the memory used. There's a PID subsystem, which controls the processes, and so on. And then if somehow the process exceeds the memory limit, there will be an out-of-memory error, and it will either keep emitting out-of-memory notifications, or it will get killed. And if you want to set cgroups, there's a lot of fluff that comes around it, but essentially it's you get the directory from sysfs cgroup, and then you set the PID max as 20, which will mean that you have 20 PIDs. Oops, sorry. So I had a demo after this. This talk turned out to be really short. I'm sorry about that. But yeah, so sorry. I'll go on to the conclusion, which is that containers aren't really magic, so anyone with a Linux machine can play around with them. And tools like Docker and Racket are like just wrappers around things built into every modern kernel. So, but having a better understanding of like the technologies that we use every day will help us debug them later. And also, like Rust is a lot more powerful, like empowering than C and C++, because it follows the adage that if it compiles, it will run, it will not fail on you and give you sec faults later. And that is fairly empowering, and Rust gives you these tools to wrap these abstractions, wrap like your operations in safe abstractions. So meaning what once was like code comments, you can now put into code. And if you were doing something similar in like C or C++, there'd be so many times where you'd have to like do the memory allocation and take care of freeing up that memory and allocating that memory, but you don't have to do that in Rust. And this, like C and C++ could be fairly intimidating, but because Rust lifts this off the weight off your shoulders, it's a lot more helpful. And yeah, and systems programming is not that hard if it's made more accessible. Yeah, thank you. Yeah, that's it. So no, my camera's not running.
Anybody has questions? Raise your hands. Don't fight each other. No questions? Francesco.
What's your view on containers in 5 years' time?
I don't think I'm the right person to be asked that question, but I guess the thing, yeah, I think they'll still be around. And if they make certain things a lot more easier, which were not, like reproducible builds are so much easier because of containers today than they were before. But I don't know what's the future.
Can you repeat his question?
Sure.
Can you ask the question?
If I wanted to play around with Rust, like containers, like do you have any resources or like toolkits or anything you recommend using to
Sure.
get started?
Yep. So the question was if you want to play around with Rust on your own, like do systems programming in Rust or generally Rust?
Both.
Okay, so.
I'm into Rust. I'm interested in the idea of like playing around with containers and getting to just with the underlying. So if there's like online resources or sort of tutorials and things that you can do it, that'd be great. Is there anything you know about that?
Sure. So there's a book called Rust in Action, which is actually about systems programming in Rust. And it's like a very good introduction to Rust. And I am no way like benefiting off it. It's just a really good resource. And the Rust programming community is very helpful. And the compiler also is very helpful. So if you get started with like the Rust book, like or Rust in Action, that's really good.
Questions?
Yeah, sure.
Any other one? Okay. Thank you for your talk.
Cool. Thank you so much.